Hello, everyone. Uh, Now, starting in semester 2, we are going to start talking about the mole, which is a very, very, very important unit that we use all the time in chemistry. So, to really explain what the mole is and what it means, we need to discuss how we measure matter. And we can do that by kind of relating it to things that you already know about. For instance, you know what you call a dozen donuts, right? 12 donuts equals a dozen. What's 12 dozen donuts? That's a gross. 2 socks is a pair. 2 people in a relationship, a couple. So we use units to kind of classify things into groups all the time. And we as scientists needed a way to count atoms and or particles as well, because there's millions and billions and trillions of atoms everywhere. So we needed a way to kind of group them. So the mole is the unit that we use for atoms or molecules that are so small that a pair, a dozen, a gross, that's not enough to really classify them into a group. Because if we tried to classify groups of atoms into pairs, we would still end up with trillions and trillions and trillions and trillions and trillions of pairs. If we were trying to tell you how many atoms are in a table or something, we would end up with too big of numbers to deal with. So a mole is going to be our unit that's the base unit for measuring the amount of a substance that's there. And that doesn't necessarily mean the amount of atoms that are there. It could be the amount of molecules that are there, the amount of particles that happen to be there. So you can use a mole to say, hey, there's a mole of something here. Avogadro's number is 6.022 times 10 to the 23rd power. Avogadro is the guy that came up with the number, the mole. And that is a ridiculously large number, Like if you had a mole of money, if you had 6.022 times 10 to the 23rd dollars, you could spend $1 million every single day for the rest of your life and not get through it. That's how big and how ridiculous the mole is. If you had a mole of pretty much anything, you could cover the earth several 100,000 times. Like if you had a mole of textbooks, you could cover the earth so many times. It's unfathomable. So a mole is a very large number, is basically what I'm trying to get across to you. So this is Avogadro, the guy that came up with the mole. I really do not understand why this is the most popular picture of Avogadro, or I guess drawing would be a better word, because honestly, this picture has always reminded me of this picture. He was a smart guy, let's say that. He was a very smart guy, and he came up with the mole, which we use every day. So nothing but respect for Avogadro. I just wish that they had used a different technique of drawing, maybe put him in a different position when they were drawing him, because honestly, every time I see this, I just think of Gollum. So this here is called a mole map. This is going to be another one of those reference sheets that I give you and you have available to you to use on tests. So there's a couple of parts to this. For this first part, we're going to be using this part of the table, not the whole thing. When we get to stoichiometry, we will use the entire mole map. But for now, we are just going to be using this left half. M, this capital M here, is going to be molar mass of a compound. So you can find M here. The little n is going to be the number of moles in a balanced equation. So again, that we're going to use later, so you don't have to worry about that one right now. The big N, which you can find right here, is Avogadro's number, 6.022 times 10 to the 23rd power. But why do you care? Why is that important? The reason that that is important is because if you are converting between mass and moles, you need the molar mass of whatever it is that you're dealing with. If you are converting between moles and atoms, you are going to use Avogadro's number to do it. So if I were to ask you to convert between mass and atoms, you would need to go from mass to moles and then from moles to atoms. So you would need both in that situation. And again, I'm sure that that was very confusing, but we will do lots of practice going forward. Okay? So moving on, looking at this first example problem, it's asking you how many molecules are in 3.5 moles of sucrose. And the hint is it's just a conversion. So I hope that you weren't hoping that the T-chart would disappear forever. It hasn't. We're going to use that for the rest of this class. So the very first step in figuring out how many molecules are in 3.5 moles of sucrose is to draw a nice T-chart out. Then, if you recall from when we did conversions way back when, the first thing that you have to do is you have to take your given number and you have to write it in the upper left-hand corner. So luckily in this problem, I only give one number, 3.5 moles of sucrose. So your job is to write 3.50 moles of sucrose. If you recall, in the bottom left-hand corner, we always write our placeholder 1. In the upper right-hand corner, we always write the unit that we're trying to find. In this case, I want to know how many molecules, so we're going to write molecules in the upper right, and we write the unit that we're trying to get rid of, or we're converting out of, in the bottom right. So in this case, moles of sucrose is going to be our unit there. Because when you do that multiplication and finally divide, this unit here will cancel out with that unit there. Okay, now all that's left is to fill in our conversion factor. So if we look back at our handy mole map up here, I'm trying to convert from moles to molecules, which I'll grant you is not on this chart, but when I give it to you in class, I'm gonna have you write number of molecules right underneath there, because you can not only convert from moles to atoms, but you can convert from moles to molecules in that same way. And you're gonna use that big N number, 6.022 times 10 to the 23rd power. So our conversion factor is for every 1 mole of any particular substance, there are 6.022 times 10 to the 23rd power molecules in it. Okay? So then we are going to multiply straight across everything on the top. So let's just do that on a calculator real quick. Performing that operation on a calculator, I get 2.1077 times 10 to the 24th. On the top, we have our moles and our molecules multiplying across. On the bottom, we're going to multiply straight across the same way. 1 times 1 is going to be 1. And then we have our moles as well on the bottom. Now what we have to do is we have to start crossing stuff out. Our moles cancels our moles. Anything divided by 1 is in fact itself. And we have to put sig figs in the equation. So in our problem, this has 3 sig figs, so our answer should have 3 sig figs, and we are going to go ahead and round this number to 2.11 times 10 to the 24th molecules. So we have just done a conversion from moles to molecules using 1 mole equals 6.022 times 10 to the 23rd molecules or particles or atoms as our conversion factor. Next, we have to kind of think logically here for a second. Mass and the mole. Would a dozen limes have the same mass as a dozen eggs? The answer to that is quite obviously no. You know that by looking at it. But you may not have thought before about the fact that the same amount of 2 different atoms is not going to have the same mass either. So if you had 1 mole of hydrogen gas, that's not going to weigh the same as 1 mole of gold, because hydrogen and gold have 2 different weights, 2 different masses. So it works the same way. Molar mass is the mass of 1 mole of an element or compound. And the unit for that is always going to be grams per mole. And so you are going to find molar mass on the periodic table. So let's just talk for a second. Let's look at the periodic table so that you can find where you're going to figure out molar mass, okay? Now, if we look at the periodic table, I know it's kind of small, but you'll still get the idea, and you can look at your own periodic table as I go along. If I want to know how much 1 atom of carbon weighs, I would go over and I would find carbon, and then I would look down at the tiny number underneath carbon, and that is carbon's atomic mass, okay? So we know that 1 atom of carbon is 12.011 atomic mass units. Okay, so that's 1 atom. But the nice thing is that 1 mole of carbon has a mass of 12.011 grams, meaning carbon's molar mass is 12.011 grams per mole. So this unit right here, what that means is in any 1 mole of carbon, you have 12.011 grams. And that sounds like a conversion factor to me, which is exactly what it is. You will find the conversion factors, how many grams exist in any 1 mole of any atom on this periodic table, because it matches their mass number, okay? So if I wanted to know what the molar mass of a compound is, all I have to do is add the gram amounts, the mass amounts of every atom in this particular compound. So let's look at what we're dealing with here with CH4. For CH4, in this crude drawing, we have 1 carbon atom and 4 hydrogen atoms. So to figure out what the molar mass is, we take the molar mass of our 1 carbon atom and we add 4 of the masses of hydrogen, okay? And in the hydrogen case, 1 hydrogen atom weighs 1.0079 grams, okay? So since we have 4 hydrogens, we're going to multiply that number by 4. So if I added all these together on a calculator, I would find that the molar mass of CH4 is 16.0426. Okay, that is the molar mass of that compound, and I figured that out by addition. Okay, so this is not going to be very complex. All you have to do is find your elements, find how many of them are in the compound, and add together accordingly. Now, once again, we're going to need to do converting with this half of the mole map. So when I give this to you in class, you're going to want to mark it up, okay? So this is a slightly bigger picture of the periodic table and as it relates to the mole map. So once again, let me point this out. If I have a certain mass and I want to know how many moles that is, I am going to divide by the molar mass. Okay? If I have a mole amount and I want to know how much that weighs, I'm going to multiply by the molar map. So you can see the arrows kind of going this way and the arrow going that way. On that side, that's how you're going to use this. If I want to go from moles to mass, I am going to divide by the molar mass. If I want to go from mass to moles, that way, going down, I'm going to multiply by the molar mass. Okay? Now, let's say I have a mole amount and I want to know how many atoms, particles, or molecules that is. In that case, to go from moles to number of atoms, I'm going to multiply by n. If I have a number of atoms, particles, or molecules, and I want to know how many moles that is, if I want to go this way, I'm going to divide by n, by 6.022 times 10 to the 23rd power. So again, when I give this to you in class, you better mark it up so that you don't do it the wrong way. So let's practice for a second. How many grams of copper are in 3 moles of copper? So right away, you should be able to identify that this is your given number. We're going to set up a T-chart. 3.00 moles of Cu is our given number. We put our placeholder 1 right there. And now all we need to do is fill in units and our conversion factor. I want to know how many grams. So grams is the unit that we're going for, grams of copper specifically. I'm starting with moles and I want to convert out of moles or get rid of moles. So moles of copper needs to go on the bottom. Okay, so that's my skeleton. Now all I need is my conversion factor. And to figure out what my conversion factor is, I'm going to go ahead and go over to the periodic table and I'm going to find copper and look at that little number right below the name of it. And it says 63.546. So I know that for every 1 mole of copper, it weighs 63.546 grams. Okay, and that is how you're going to fill in your conversion factor. Then we're going to plug that multiplication into the calculator, divide by everything that's on the bottom, cancel our units, and get an answer. So when I plugged that into a calculator, I got 190.638 grams of copper. Because again, this is going to cancel out with this. Grams is going to be our final unit. Anything divided by 1 is going to be itself. But we are absolutely not done because we have to pay attention to sig figs. There are 3 sig figs in that given number. Therefore, our answer has to have 3 sig figs. So we're going to round that off to 3 sig figs. So this entire number is going to round to 191 grams of copper in 3 moles of copper. Okay? That is going to be your final answer. Moving on. Now we need to go and do a practice problem for mass to atoms. So if we're looking at our mole map, we want to go from here to here. You can't go directly from here to there. That does not work, okay? So we have to go from here to your middle part, from here to there, and from there to there, okay? So our T-chart needs to be a 2-step T-chart. So instead of the singular T-chart that you're used to, it's gonna look like that instead, okay? It's going to get extended just a little bit. Now, this is going to work the same way though. This right here is why it's very important to keep track of your units. It is paramount that you keep track of your units. Otherwise, you are going to lose track of what is going on in here. Okay, so once again, our first step is going to be writing your given number in the upper left-hand corner. So our 31.1 grams is going to go in our upper left. We put our placeholder 1 right there. Our first conversion has to be going from mass to moles. So we have moles right there. Grams is going to go down there. Okay? If we look at our periodic table, we find that for every 1 mole of gold, that has a mass of 196.97 grams. Okay? So imagining that we just did a one-step conversion, we would now be in moles of gold. How many moles would be present in this amount of gold? But we're not done, right? We're not done. So what we need to do next, because I'm not asking for moles, I'm asking how many atoms, is I need to go from moles to atoms. And to do that, I use Avogadro's number 6.022 times 10 to the 23rd power. So atoms is our unit that we're looking for. We are in moles due to the conversion we just did, so moles needs to go there. Our conversion factor, our N, says that for every 1 mole, there are 6.022 times 10 to the 23rd atoms present. So to solve this, we are going to multiply everything together on the top. We're going to multiply everything together on the bottom straight across, and then we're going to divide and solve. So doing some quick calculator work, I multiply 31.1 times 1 times 6.022 times 10 to the 23rd power. I get 1.872842 times 10 to the 25th on the top, okay? On the bottom, I have 1 times 196.97 times 1, so I'm just going to get 196.97 on the bottom, okay? Then I'm going to divide what's on the top by what is on the bottom and solve. And doing some quick division, I get 9.508. There was the bell with a bunch of other numbers, times 10 to the 22nd atoms. We would round this off because in our given number, there's only 3 sig figs, so our answer has to have 3 sig figs, so we're going to round that to 9.51 times 10 to the 22nd atoms. And that would be our final answer. So I hope that was helpful. Feel free to ask me questions in class.